Hello, everybody. This session is dedicated for autonomous operations. Autonomous operations is the main subject of the session and the possible impacts of these new USB systems in terms of people exposure, apex, carbon emissions, and a lot of other variables. Many operators, including Total, which is my company I'm going to present myself now, are evaluating the opportunities of pilot testing in their installations before possible large implementations. So just to introduce myself in the beginning, I am Ahmed Sabah. I'm responsible for ROV operations in Total, which deal with all operations in from drill support to exploration, production, and interventions, and IMR operations, and everything related to ROV operations. And we would go for round table with this session with everybody, starting with we'll start with Matt, and then we go on in the session, continuing one by one for the session operation. So we'll start with Matt. Raise your hand, Matt.
Hey.
And then Al Romson is for Solmura Subsea, and then Ocean Infinity Group. We have Michael King, and then last and not least, Duncan Mallas is from X-Ocean. So we'll start with Matt's session. Matt, can you start with a small presentation of yourself and then carry on with your presentation, please?
Sure. So I'm Matt Bates. I'm the products director for Saab CI in the UK. Been with the company quite many years, working on the design side and also sales side. And my presentation's about some of our enabling technologies which are working towards our new robotics. Let me share my screen. Okay, so I'm going to talk about some of our developments that are enabling our next generation of smart underwater robotics, and specifically how these smart robotic solutions will reduce the dependence on vessels and people offshore to save cost, increase safety, and reduce the carbon footprint of underwater operations. I'm going to talk about our developments from the perspective of 4 types of robotic vehicle operation. So firstly, I'm going to talk about developments associated with conventional tethered electric ROVs. Electric ROV systems have been the mainstay of inspection, survey, and light work, but increasingly we're turning to electric solutions for even greater work capability. Next, I'm going to present some developments that facilitate the operation of ROVs that are hosted from unmanned surface vessels or lightly manned surface vessels with some or all of the operating personnel onshore. Then I'll present some developments that we're doing with our hybrid AUV ROVs, the Sabertooth, which can perform all inspection, monitoring, and survey tasks, either fully autonomously or by supervised autonomy through low bandwidth communication links, either from a vessel or from onshore. And then finally, I will show some recent developments towards fully resident, autonomous, hybrid, and remotely controlled vehicles that are located on the seabed for extended periods of time, also with control from onshore. Whatever the operational scenario, or indeed the market sector, whether it be offshore energy, defense, marine science, or others, the drive with these developments is much the same. It's to increase the operational value of the robotic system through the reduction of operating costs, increasing work capability, reducing human support, increasing endurance and persistence of robotic systems, whilst at the same time reducing risk and impact on the environment. These are some of the key enablers that support this plan, and I'll touch on developments relating to most of these during this presentation. So firstly, looking at the development of conventional tethered electric ROV systems. Observation tasks have been the domain of the electric vehicle, while survey and work tasks have generally been the domain of the hydraulic vehicle, and this has been slowly changing over the years. Electric vehicles first started life as pure inspection vehicles carrying a camera and maybe a sonar, but they soon grew in size and capability and intelligence, and before long, compact work vehicles were introduced that could carry a reasonable amount of tooling. And so the lines between observation and work class vehicles started to become a little blurred. Today, we have proven autonomous vehicles that can carry out extensive survey work, and electric work vehicles that can perform all but the most demanding of work tasks. So what's next? Well, the next logical step is the development of a full-blown electric work vehicle that can carry out all tasks conventionally done with hydraulic work vehicles. There are already several fairly large and capable electric vehicles working in the market today, and our latest development is an all-electric equivalent of a 250 horsepower hydraulic vehicle. In this case, it has electric manipulators. So why go for an electric solution? Well, apart from generally having a lower cost of ownership, there are quite significant environmental benefits. Less oil, lower risk is a benefit, and they're generally more efficient, requiring less power, which for some of these modes of operation is really important. Another key reason is that it's easier for more digitalization and automation, which really helps unlock these remote and autonomous modes of operation that I'm going to talk about. One of the main challenges, however, for the electric work vehicle is tooling. Much of the tooling on the market today needs a hydraulic supply. However, most tools actually require a relatively small amount of power compared to propelling the vehicle. So a relatively small HPU can be used to deliver what's required for most tooling. In the past, the challenge with electric thrusters has been the power output when compared with hydraulic thrusters. To date, most electric thrusters have lagged behind hydraulic in terms of performance, but our latest SM14 thruster is able to produce a higher thrust output than a similarly sized hydraulic equivalent, so it's a win-win with higher efficiency and higher thrust. But to really maximize the potential for electric vehicles, the tooling needs to be electrified as well. Electric tools for some tasks, such as cleaning and pumping, have been around for a while, and several electric torque tools are now available, which are smaller and lighter than their hydraulic equivalent. But a key development has to be the manipulators. Today, with the rapid advances of robotics above water, there are less technical barriers to achieving the required underwater ROV performance. The image on the right is of our latest 7-function electric manipulator, which exceeds the capability of the current industry standard hydraulic manipulator. Being electric, it has the same benefits as a hydraulic vehicle. This video shows the EM17 electric manipulator in action. One of the key things about this manipulator is the repeatability of its position. And this is really important for developing autonomous and step-by-step semi-autonomous operations. It's been something that's been talked about for quite a few years, but the next developments relate to ROVs and vehicles being hosted for unmanned and lightly manned vessels. It's really starting to gain traction in the industry and is a significant cost saver. To illustrate Saab's developments, I'm going to talk about a multi-shot mine neutralization system, which is a defense program developed to produce an ROV deployed over the horizon from an unmanned surface vessel. It's a joint UK-French development program involving Thales, ASV, and Saab. The objective of the system is to be able to relocate a potential mine found via sonar, identify the mine type, and then dispose of or immunize and support recovery operations of that mine. One of the biggest challenges is that those operations have to be conducted in up to 4 knots of current and up to 300 meters water depth. Another big challenge is that it has to conduct operations over the horizon, away from the mother MCMV vessel. Whilst a vessel is still required today to control the unmanned surface vessel and the ROV system in this particular case, the main benefit of the system is to take that $200 million vessel away from the minefield and, more importantly, remove the operators from the vicinity of the minefield. As I say, one of the biggest challenges was the need for over-the-horizon operation via a radio link. The link between the host USV and the mother vessel suffers from relatively low bandwidth at 3 megabits per second with a latency of 250 milliseconds. And in bad weather, 100% uptime cannot be guaranteed. Whilst the vehicle is remotely controlled with a human in the loop, the MCM vessel personnel have much else to concentrate on, apart from the complex task of flying and remotely controlled vehicle that's located miles away. The solution called for a change of mindset from a conventionally controlled vehicle to an autonomous vehicle with closed loop positional control that can be supervised by a human rather than directly controlled by the human. The MCAMV operators potentially managing multiple assets at the same time and potentially not being ROV experts require the use of autonomous behaviors during the operation and launch and recovery. Here, hopefully, you can see the system undergoing sea trials. Firstly, there needs to be a command decision to prepare and then launch the vehicle once the USV has arrived on location. The winch, tether, and vehicle all have to be managed simultaneously to ensure no tether entanglement with the USV thrusters. The vehicle executes the launch automatically and then goes to a safe distance from the unmanned surface vessel. Next, the vehicle transits to the suspected target with waypoint navigation and obstacle avoidance. And then the mine inspection is then automated, and any engagement with it is handled by step-by-step control. Having placed the charge, the vehicle transits to the next target, repeats the cycle, and then ultimately, having deployed 3 charges, returns to the USV for automatic recovery and reloading. There's a need for fallback behaviors should the comms link fail and to minimize the operator workload. So returning to the USV for recovery also needs to be automated. Another similar program we've undertaken is with Boeing for a submarine launch vehicle system. The aim of this system is to be able to conduct inspections or intervention tasks anywhere from deployment from a submarine that can travel for some weeks, covering a distance of thousands of miles. The removal of a large surface vessel and associated crew obviously has the potential to save substantial operating costs, as well as the possibility to conduct discrete operations. Due to the remote nature of the submarine, the comms link to the submarine is via a satellite link. And in order to operate over that kind of link that has limited bandwidth and very high latency, the advanced vehicle control system allows for station keeping, again, with measured step-by-step control and point and click operations to guide the vehicle to the task. Meanwhile, a single video and sonar link are transmitted back for confirmation of the last control inputs before taking the next step. A smaller vehicle, a conventional Falcon ROV, has also been deployed from an unmanned surface vessel, and larger work vehicles like the Leopard are soon to be deployed from yet larger unmanned vessels. The next developments I'd like to share with you is on our Sabertooth hybrid vehicle. The aim here is to develop systems capable of performing all inspection and monitoring tasks with and without the human in the loop, as well as the further development for some light intervention capability. The Sabertooth is a fairly mature product now and is used in 3 modes of operation. There's a pure AUV, acting as an ROV with a tether for some applications, and finally as a hybrid, where step-by-step control is achieved via a Bluecom free space optic modem or an acoustic communications link. As well as its long-range endurance, it has 6 degrees of freedom, allowing it to stop and hover for anomaly investigation, for example. Many of you have probably seen this video already, but it's the best I have showing the capability in clear water. And although it's a few years old now, it's still very relevant to the developments of today. So what are the challenges? Well, industry adoption is one challenge. There are now quite a few systems operating, but most are conducting fairly shallow water survey operations. Another big challenge is working at depth. Recently, we've been running both autonomous and tethered operations at 2,000 meters at speeds of up to 4 knots, whilst maintaining basic communications and positioning from the surface. The high-speed descent of this kind of vehicle is typically 3 times the speed of a winch, so operating without a tether can improve operational efficiency. The final development I'd like to talk about is subsea resident vehicles being installed long-term on the seabed. Vehicles of both the autonomous and semi-autonomous variety, resident on the seabed for extended periods, again have the obvious potential to save significant vessel costs. One of the key enablers for residence systems is docking. And here you can see both an in-house developed docking station on the left and the Equinor standard docking station on the right. In order to control, charge, upload and download mission data, a safe vehicle dock is required, and there is benefit in finding and locating the docking station autonomously, either for efficiency or in the event of a loss of communications. In these 2 examples, docking is controlled by a pilot using step-by-step controls through a Sonodyne Bluecom free space optical modem, and data download and charging is achieved using the BlueLogic inductive connector. To show the docking for real, I have a short video. In this clip, you can see the vehicle and docking garage in a clear pool for illustration, but it's routinely conducted at sea. This is in manual control, but it's already been successfully done many times autonomously using the docking garage arrangement with twin acoustic transponders mounted on the mouth of the garage. You can see the BlueLogic connector mating with the docking garage configuration for data charging, data transfer and charging. In the second clip, the vehicle is docking vertically to the Equinor docking station without physical guides. This is under step-by-step control. As the vehicle undocks to fly away, you can see the Bluecom system used for transmitting the control and video link between the untethered vehicle and the docking station. And then in this final clip, you can see the mating of a torque tool on the front of the Sabertooth into a receptacle on a valve panel. Again, the Bluecom was used for control comms and video with the optical transponder mounted on the valve panel. The next step is auto docking. With further work and suitable sensors defined, it will soon be very possible to dock autonomously to Equinor's standard docking station. Several challenges have been set by Equinor, who are driving towards resident systems, and these are now being accomplished. Saab has a 3D visual-based underwater simultaneous location and mapping system, or underwater SLAM for short. And this advanced system builds up a 3D point cloud of the environment in real time. The green snail trail here shows the position of the vehicle sensor relative to the surrounding point cloud. As well as a means of object tracking and vehicle station keeping, the operator can interrogate the point cloud data in real time to help classify objects. With this accurate real-time 3D data acquisition on the vehicle possible, combining it with precise electric tools such as the electric manipulator and torque tool will soon be allowing automated manipulation of objects and valve operations to be even more efficient. And finally, the video clip on the right is from trials where an ROV system was positioned using this 3D SLAM system and automatically inserted a talk tool into a receptacle. Again, really important for low bandwidth connections. Finally, we're looking at how all of these technologies and the vehicle platforms themselves converge. Some of the work going on just now is to augment the saber-tooth hybrid vehicle with more tooling, and even to augment the ROV with batteries and autonomy to facilitate tetherless resident operations. So I hope you can see how all these developments in the electric vehicles, the manipulator, the autonomy and automation, the perception and comm systems do indeed all come together for a complete electric underwater robotic solutions that can reduce the dependence on vessels and people offshore to save cost, increase safety, reduce the carbon footprint of underwater operations. Thank you.
Thank you very much, Matt. It's a very inclusive presentation with a lot of concepts in the same place. Thank you for that. So we will run the presentations, the 4 presentations back to back, and then we will go in an open session, Q&A session. So the next one up is Al Romson. Go ahead, Al.
Great, thanks. Yep, so briefly introduce myself. I'm working as innovation lead for Somara Subsea. Joined the company earlier this year. My background, I'm a hydrographic surveyor, also spent some time in academia recently, and been working in predominantly R&D roles in the last few years. So I'll get on to this presentation now. Right, second, share screen. Okay, you've got that, right. So in this presentation, I'll briefly run through some developments I've been involved with, which have aimed at enabling autonomous subsea pipeline inspections. The project which I'll be referring to was completed whilst I worked with Swire Seabed, who have now closed down. But as part of my current role with Somara, we are building on progress made within this area, such as that which I'm going to be running through now. So Somara Subsea, we're a fairly young subsea service provider. We focus specifically on survey inspection. Central aim, as seen in the slide, is to be innovative and disruptive, thus actively implementing new unmanned survey technologies. For the purpose of this presentation, I've selected 6 core areas which need to be focused on, in my opinion, to allow unmanned pipeline inspections to be completed. Primarily, unmanned maritime systems are required: USVs, AUVs, ROTVs. Their successful implementation can remove the need for large survey vessels manned by extensive crews. Other important issues are navigation, the payload sensor data available, automation of data analysis, interpretation and processing, and ultimately automation of the UMS retasking. So an introduction to the unmanned pipeline inspection project then, that I'm talking about now. In this pipeline, surveys were completed using a Hugin AUV paired with a surface vessel as seen in this video. Hugin here was paired with the Seakit Maxilima. It was a developmental project involving multiple organizations. This aimed at developing a working solution implemented during commercial pipeline inspection work scopes completed for Equinor. Software automation was central to the project, and I worked with Ivor in this area. During the project, 2 inspection campaigns were completed for Equinor, involving inspections of 7 pipelines with a combined length of 350 kilometers. This took place offshore of Bergen, Norway. The next phase of this project, which had commenced, involved design and build of a large USV containing onboard data processing center, facilities for launch and recovery and charging of an AUV, and for data download, with the aim of enabling 30-day missions. The project was halted before this new USV was built, though, due to the closure of Swire Seabed. Other firms continuing in this work though, and as part of my current work with Samara, we are investigating options to further progress with similar developments. One recent area of focus being combined USB ROTV surveys. ROTVs have obvious maneuverability constraints compared to the AUVs, yet on the plus side, the umbilical link provides a permanent power source and means to transmit all the data back to the USB in real time. Here is an example flow diagram of the typical processes involved with unmanned pipeline inspection operations, specifically AUV-centered operations. Only part of this was relevant to the operations undertaken within the pilot projects I'm talking about now, as onboard USB data download and AUV charging was not possible, so only single dive missions were possible. The long-term plans with this larger USB, which was to be built, were aiming towards fulfillment of this entire process. So running through the objectives of the project in very brief, primary objectives of the first two phases of the project, which was undertaken, were process and procedure development for unmanned subsea pipeline inspection, utilizing the combined USB AUV survey platforms with operations control from shore. Development of software and functionality allowing pipe tracking, automation of eventing, alarm generation, automated data processing workflows, QC and analysis, navigation aiding, and in-mission retasking. Finally, reduction of post-mission data processing times through enabling processing to begin on board of the AUV and to be continued on shore. The first pilot project, or operational field trial, was completed in 2018. The aim of this was to test operational procedures for running a full survey campaign remotely from a shore-based control center. This was proved effective. The charts to the right indicate the location of assets which were surveyed, the pipelines linking Equinor's Troll field to Kollsnes base close to Bergen. Communication infrastructure was and is the enabling factor allowing such remote operations to take place. This diagram provides a rough indication of the communication lines utilized within the project. SATCOMs and maritime broadband radio forming the main communication links here. In pilot one, the CKIT Maxa Lima USB was planned for the project, yet due to a clash of timing, was not available. As a result, we needed to resort to using a manned vessel, which simulated the role of a USB. Operations were still completed in the same manner with command and control situated on shore, major change being manual AUV launch and recovery. There's the vessel which was used in, one second, sorry. Yeah. Here is an example of some of the data collected during pilot one, taken from AUV high pass at 25 meters altitude. Multi-beam echo standard data clearly reveals an area of free span detected on one of the pipeline routes. An example image of an area of interest collected by AUV payload cameras. For pilot two, we were able to utilize the Hugin paired with the CKIT USB. During missions, successful unmanned launch and recovery was completed offshore. Data acquisition was controlled and monitored from shore, and 4 pipelines with a combined length of 175 kilometers were surveyed. The operation boasted a world first for over-the-horizon commercial pipeline inspection using unmanned platforms, with pipelines being surveyed up to 100 kilometers from shore. This video was taken during pilot 2 and shows offshore unmanned recovery of the Hugin by the CKIT USB. Some data examples reveal the varying levels of detail we were able to obtain using different sensors and methods. This first image shows a DTM of a stretch of pipeline surveyed using multi-beam echo sounder, whilst the second image depicts the same area using laser data. And the third image reveals a depleted anode indicated in a 3D image reconstructed through photogrammetry processes. During the project, Ivor developed software functionality which was installed on 2 boards integrated into the Hugin AUV. During the pilot projects, the deep learning board was used primarily for pipe tracking using image data, and the workflow manager board enabled data processing to begin on board the AUV, for alarms to be communicated to shore, and for data QC and analysis. You can see below an example of the deep learning pipe tracker method implemented on the deep learning board, which ran in real time during missions. Results generated from this allowed identification of top of pipe. Further pipe tracking methods were implemented and tested in simulator dives following Pilot 2, which used multi-beam and laser data. Here's an indication of pipe tracking using image and multi-beam data, as referred to, with events generated using deep learning processes. These were labeled on screen here, and clearly reveals where a section of pipe enters into burial. Another fly through, this one combining DTM data linked to the image data on the right there. The deep learning methods developed by Ivor were implemented offline during the course of the project. That's the eventing methods, with the long-term objective of migrating these processes to the deep learning board on board the Hugin eventually. The methods proved effective in identifying field joints and anodes, and in addition to providing event listings, functionality was developed to use the detected features for navigation aiding. Post-Pilot 2, identification of anodes, then the subsequent comparison of their known and observed position could be used as a navigation check. And again, the long-term aim with this would be to use this data as an input for dynamic navigation aiding of the Hugin. The Workflow Manager board enabled alarm generation. It was possible to transmit these alarms to the surface via a low bandwidth acoustic link, which could then inform operators of a number of critical conditions, such as lack of multi-beam coverage, poor visibility, hampering collection of image data, pipe not detected, and missing sensor inputs. The alarms were used for informing the operators onshore. However, the long-term plans were to configure these outputs with the AUV control system to form operational inputs, furthering automation. The Workflow Manager board installed on the Hugin enabled data to be successfully processed on board the Hugin AUV as collected during missions, and enabled this processing to be continued onshore post-mission. An automated workflow enabled data processing, cleaning, and QC, and post-Pilot 2 functionality was developed, allowing automated processing based on pipe diameter once the top of pipe was determined from pipe tracker data. QC component advanced on the Workflow Manager board is essential to further levels of automation possible. These form inputs to decisions to resurvey sections of pipeline, for example. In the future, the outputs of such processes will form vital inputs to automated retasking procedures. There are a number of pipeline inspection specific analytical processes that were developed to run on shore, then slowly to be migrated to the onboard AUV Ivor computers. Unfortunately, these were not tested operationally in the field during the course of the project. However, simulated tests revealed how significant time saving was possible through automating pipeline digitization, tagging, data classification, and QC. I've explained to you what was achieved in the Unmanned development project, which ran between 2018 and 2020. Despite this project having ended, in the words of a great man, now is not the end. It is not even the beginning of the end, but it is perhaps the end of the beginning. Work in this field is progressing rapidly, and in the last few months at Samara, we have initiated collaborations seeking to progress this work further. The benefits to clients are clear: reduction in costs, vessel time and man hours, and reduction in environmental impact. A significant distance is yet to be covered along this road to automation though. At the moment, we're able to complete unmanned operations with humans in the loop as remote decision makers. In the near future, we aim for automatic in-mission retasking of unmanned maritime systems, allowing larger work scopes to be completed. The ultimate goal, though, is for the role of humans in this loop to diminish to a level where we are only required to oversee operations. In our work going forward to enable this, we have identified 5 key areas which need to be focused on. These are hardware development, onboard USV IT infrastructure and maritime communications, further automation of data processing in QC, navigation aiding and adaptive control, and machine learning and deep learning used for eventing, interpretation and implementation of automated change detection processes. Well, thank you for listening to this presentation.
Thanks a lot. Now we have the third presentation from Michael King, Ocean Infinity.
Good afternoon, everybody, and thank you for tuning into this session. Ocean Infinity were founded in 2016, and since then we've been working on global projects utilizing predominantly multiple autonomous and uncrewed robotic systems, really focusing on what can be achieved with the innovative and collaborative use of the most modern technology available. From large-scale hydrographic mapping to search and salvage projects in thousands of meters of water. As you know, some of our projects have made international news, but we've also conducted countless smaller and commercial projects across the world. Our ethos is that the use of multiple unmanned and uncrewed systems for force multiplication vastly increases the efficiency in project delivery. And through this, we've logged more commercial AUV hours than anyone else, allowing us to really get to grips with our own equipment and get more and more out of our technology. However, 18 months ago, we made the decision to grow a complementary, truly robotic business, further reducing offshore personnel and achieving a greater level of sustainability for marine operations. And so was born the Armada fleet. As it says there, it's a new venture for Ocean Infinity, launched earlier this year in February. And the idea is that we want to be operating the world's largest fleet of low-emission, multi-role robotic ships. An initial fleet of 21 and 36-meter vessels that can be deployed worldwide are currently under construction, and we're focusing on the significant reduction of emissions, increased safety, secure and reliable communications, and leveraging those economies of scale. We'll be deploying revolutionary fleet technology capable of shallow and deep water survey, as well as combi systems to remotely provide ROV, AUV, and UAV payloads. And as I said, with the fleet currently under construction, we will be fully operational in early 2021. Now, we want to get away from the idea that these are USVs. Yes, they are uncrewed. Yes, they are surface vessels. However, they're a very different beast to the traditional sub-15-meter USVs currently on the market. They're proper ships. They're being built at a proper shipyard in Norway with a rugged, ocean-going design, and they'll be capable of handling sea states comparable to larger traditional survey vessels. Initial vessels are being built in 2 classes. As you can see, the A21 will be capable of holding station, but will not be a certified DP vessel, whereas the A36 will be fully classed and certified DP2. They'll be capable of transoceanic passage with extended range and weatherability, and are classed and assured as you would expect of a vessel of this size. One further point to note is they'll be flagged in the UK, and to take advantage of the world-leading focus on marine robotics and uncrewed systems that we have here in this country. Now, as you can see, our first vessels are under construction in Norway, and as I said, they will be delivered in early 2021. That's the first 2 vessels, and then we have a program of launches scheduled throughout the year to deliver the full fleet. Now, we're working really, really closely with the shipyard, even in spite of the coronavirus pandemic and everything else, to ensure that when these vessels launch, they will be as good as they can possibly be from day one. We want to be able to commission them, test them, and press them into service for our commercial clients as soon as possible. Now, just a little bit on the payloads that are going to be possible from these vessels. Each one will have a suite of survey equipment permanently installed in a subsea gondola, and this ensures some of the highest possible data quality. The existing USVs on the market with the best hydrographic data that we've seen come from gondola-based systems. It creates the best hydrodynamic environment, it creates the quietest acoustic environment, and it improves the sea state capability of the vessel. In addition to that, that survey gear that'll be permanently installed, the idea is that we will be able to deploy modular payloads to each USV, to each robotic ship. These will start with things like moonpool deployed work-class ROV systems. You heard from Matt that we're looking at using some of the Saab Leopard electric ROVs that he spoke about, but we'll also be repurposing some of the existing Schilling HD hydraulic systems that Ocean Infinity already own. And this will give us work-class ROV capability down to 3,500 meters water depth. We'll also have single and dual vehicle options on the larger vessel, on the A36, and this will increase our mean time to critical failure. As well as that, we'll be deploying hydrographic and geophysical payloads, towed side-scan sonar or synthetic aperture sonar, magnetometers. We have plans for UXO capability as well to provide that hydrographic and geophysical survey suite. And the third one that you can see there is that we want to be able to deploy deep water multi-beam for full ocean depth monitoring. For transoceanic and deep water surveys. Now, we know that the Remote Operations Centre is the hub of any uncrewed operation, and that's certainly true of the Armada fleet. And as such, we're currently constructing a state-of-the-art facility in Southampton on the south coast of the UK in order to provide us with that remote operations capability. The word autonomous gets us into a little bit of trouble. It's certainly the roadmap for the next 2 or 3 years to be able to offer these vessels as autonomous with having some decision-making ability taking place on board. But in the first instance, we will certainly be supervising and controlling our ships 24/7 with a one-to-one watchkeeping setup with qualified mariners. In addition to this, we will have shore-based online and offline technical crew, as you might imagine, and we will rely on human-in-the-loop operations at all times. We're not removing the staff, we're onshoring them. The team will still be relying and working on these vessels around the clock, but they will be sat in the operations center rather than offshore. But of course, this brings new and very different challenges. At Ocean Infinity, we're focusing really strongly on cybersecurity and reducing the disruption to operations that might lead to. And we're really keen on providing a robust, secure, and redundant link to each vessel. All of this allows for essentially the greater levels of comfort for the crew. They will suffer less fatigue from being removed from that harsh environment. There'll be less travel and time away from home, as well as being able to work in an environment with more facilities. But above all, there'll be easier access for clients and other stakeholders to monitor and become involved in project operations. Reduced international travel also protects against difficulties that we've become all too aware of in 2020, and further leads to a greater level of sustainability that I'll talk about in a moment. We also know that data management and data handling is absolutely key to our business model. At Ocean Infinity, we've got a huge amount of experience handling huge data sets, but the Armada fleet requires a slightly different focus and, above all, increased satellite communication ability. It's pretty clear that Remote Operations Centers hinge on not only that advanced data handling, but also on that bandwidth link between the ops center and the ship. Now, you can miniaturize pretty much anything in electronics and robotics that you want these days, with the exception of a satellite dish. The sad truth is that the larger the satellite dome you have, the greater bandwidth you have to communicate with your vessel. And because we're building larger uncrewed systems, we have the ability to take larger satellite domes offshore with us. And that enables us to have larger bandwidth, enabling true command and control and data transfer in near real time. But it's also important to have that as a very secure cloud-based IT infrastructure, not only in terms of communication with the vessels, but to allow other remote working setups, remote data transfer, and client and stakeholder interaction at the earliest possible stage of a project. Now, we're putting in some pre-processing steps in all that we do, using some machine learning and automation tasks on board the Armada fleet itself, which means that the data will have undergone a series of pre-processing steps before a human has even seen it. And this, along with advanced compression techniques, then allows the data to be brought back in packets in near real time for validation and QC, allowing that analysis I referred to earlier to begin earlier in the process. This is particularly useful for survey and inspection work that informs further campaigns and will allow the shortening and truncation of offshore campaigns even further. However, as we increase the level of automation and remove some of the subjectivity in that data processing, we're also adding an enhanced level of confidence in the data sets themselves. And we'll do this by providing performance statistics from individual sensors and software packages. This will show that sections of data that may or be in or out of scope, and will give quantifiable quality information to ensure that world-leading data quality that Ocean Infinity is known for. We can do things like show instant coverage plots and acquisition statistics to highlight any areas of poor data quality for further review. Or, as I said, on inspection tasks, we can highlight those areas of interest at the point of acquisition to ensure that the most useful and valid data set is indeed presented. Something else that we're hugely proud of at Ocean Infinity is our commitment to sustainability. It's something that we believe should be truly at the heart of everybody who operates in the marine environment. And as such, we've built the Armada fleet with a huge focus on sustainable credentials. So we've done some pretty advanced tank testing based on the Armada robotic fleet ahead of delivery. And we will be validating these numbers as soon as the vessels launch in early 2021. But on the left there, you can see a graph of CO2 emissions based on a typical offshore 21-day campaign. This has been modeled on a mixture of vessel transit, survey works, and time on DP, and a little bit of standby, looking at the fuel burn statistics associated with that. Now, when you burn marine diesel, you suck in oxygen and you expel CO2 at the rate of about 3.2 kilos of CO2 for every kilogram of fuel burned. And that's why the disparity between CO2 emissions is even greater than that for fuel burn itself. Now, we can break down the advantages into three different sections. Firstly, there's a reduction in vessel propulsion requirements. This is fairly simple to understand. The Armada fleet has brand new diesel hybrid engines. They're smaller, they're lighter, and you're not having to carry around a superstructure acting as a hotel for 30 people. The vessel design focus also shifts to a data quality model, allowing data to be collected from that smaller vessel, and all of that adds to a lower fuel burn and therefore a lower emission statistic. The second section is those personnel requirements themselves. You're not running a hotel for 30 people. You're not running the galley, the climate control, the gym, the sauna. And because the disparity between onshore and offshore power generation is so inefficient, running that op center and running the facilities for those 30 people onshore is far more efficient and requires far fewer emissions than it would do using marine generators offshore. And lastly, there's no requirement to change the crew every 28 days. There's a reduction in flights around the world, there's a reduction in transit time, and above all, there's a reduction in the carbon footprint of port services that are used during a crew change. So adding all this up, it gives more than a 90% reduction in operational emissions. And through an active reforesting scheme that we're a part of, it actually enables us to offer the Armada fleet as a carbon neutral option for offshore survey. We've already committed to planting over 73,000 trees in the Scottish border region, and this will facilitate the capture of more than 21.5 million kilograms of CO2 over the next 18 months. However, as in addition to us offering new services as the most sustainable we possibly can, we've also got a huge focus at Ocean Infinity about being more sustainable with our existing technology. It's important to minimize our existing environmental impact, not just our environmental impact moving forward. Therefore, during 2020, we've already eliminated single-use plastics from all of our sites and vessels around the world. We're constructing our new Southampton Operations Centre to the government's new A17 rating for sustainable businesses. This includes things like a full waste management plan and a biomass power recycler on site. Even before the coronavirus pandemic, we were minimizing air travel emissions by reducing business class travel and investing in some of the best conferencing facilities and video conferencing that we could. We've partnered with a UK seagrass regrowth platform to help facilitate the creation of new marine environments. And we're collaborating with various worldwide universities to look at ways to improve sustainability and scientific understanding across the marine sector. Now, all of this innovation and our future capabilities aren't without their challenges, and we know that. We don't want to remove the personnel from the offshore environment if the data product suffers. At the end of the day, it's the data and the answers provided that are the most important thing in the world in which we live. And unless we're providing that world-beating service, then it doesn't matter how efficient or green the solution is if there is a drop-off in data quality. So striving to ensure reliable communications that enhance data delivery and the model by which offshore services are offered, in addition to the safer, more efficient and greener methodologies uncrewed ships provide, shows that the future of offshore operations can indeed be considered to be uncrewed. The second challenge, and probably the larger one, is regarding the regulatory challenge. And we continue to work hard with the MCA, the US Coast Guard, and other international governing bodies towards safe operations of these larger robotic vessels. We're working with classification societies such as DMVGL, and we're grateful for support from the likes of the IMO and the MSC as we really push the boundaries of what is technologically capable. The other important thing is we're trying to shape this industry ourselves, and we take an active role in the creation and adaptation of codes of practice, such as the Maritime UK and IMCO codes of practice. But by taking active roles on these steering groups, we ensure that the regulations are not only fit for purpose in keeping existing and future contractors safe and operating legally, but they serve the industry sensibly as well. We want to create a world that we can all operate and all pass on the benefits of these uncrewed systems to all the stakeholders without being strangled by regulations that don't work for the vessels that they're deeming to regulate. So in summary, once we have this fleet of robotic ships in early 2021, built with modular payloads and capabilities, they will be utilized across a wide range of industry sectors and tasks. And we're really looking forward to getting stuck into some challenging projects. So thank you very much for listening. I appreciate that there isn't the option for live Q&A in this format, but if you should have any burning questions that have arisen from my short presentation there, please feel free to give me a call or an email on the details on screen there, or reach out on LinkedIn. And I'm looking forward to sharing more information about the Armada fleet and what we're trying to achieve. So that's all from me. Back to you, Ahmed.
Thank you very much. We actually are looking closely in your project in total in terms of the Armada project and the deliverables that we are expecting in the beginning of next year. And we are expecting a good surprise from your side. So we hope I hope we hope so. Okay, now it's time for our fourth presenter, which is Duncan Mallis from X-Ocean.
Good afternoon, everyone. My name's Duncan Mallis. I'm the Chief Strategy Officer for X-Ocean. X-Ocean are we're a ocean data company, and this allows us to basically conduct operations and we're only using unmanned technology to conduct our survey operations. We're operating our services to other survey companies, but mainly to energy major contractors and companies, and also to government agencies. Being one of the first companies to offer an unmanned service, we sort of try and de-risk it for the clients. So we operate the surveys as a fixed price, all-inclusive turnkey operation, and we guarantee the quality of our data delivery and the quality of that data. The previous speakers have spoken about how the different scenarios of why you want to use a USV. Safety is always the thing that's most closest to all of us, and having no offshore personnel makes it obviously a lot safer. But the one that's almost as important at the moment and is gathering more momentum is the whole environmental impact and ultra low emissions. Michael was saying about how the Armada fleet's got going in lower and lower. We use 10 litres of diesel a day per boat, so it's less than you would normally use to drive your car into work almost. So we're a carbon zero company from the outset. And because we're not moving people, we're not burning lots of fuel, we're able to operate this service as a significant saving to a normal manned operation. We've been operating since towards the end of 2018. And in that time, we've operated in these areas around the world for those clients on the left there. Bear in mind that all these locations we're going to, at all times, the vessel was piloted by our team of remote USV pilots in Ireland and the UK, and the online survey was done from the UK and Ireland as well. So at no point in time do we have anybody out there. We used to have a field operations or just a simple 1 or 2 person field crew out there, but even now, because of COVID, we're shipping the vessels already equipped, 20-foot containers. We're operating with local teams to take those containers, take the boats out, put them in the water, conduct a few tests, and then hand over the operations in the water to us. So we go out, do the survey work, come back and repeat the process. So we don't need to have a support boat. Sometimes regulations require it, but for 95% of the work that we've done, we haven't had a requirement to have any support boat on there. So it's a truly over-the-horizon global survey service that we provide, but basically based using our team of people in the Ireland and the UK. And also in Canada, we have an operations office over there as well. So a little bit about our technology. We have the largest commercial USV fleets currently operating. We're up to 9 of the XO 450 class that we have. We have 2 more in production this year. We're also working on larger USVs as well. These are pretty much the size of a large car. They're 4.5 meters long. They weigh just under a ton, so they fit in a 20-foot container. But that doesn't mean to say they're anyway, they're not very capable. These vessels are, well, we've put them in a test tank to 6 meter seas. We've actually operated them in Force 8 in the North Sea. We've collected fantastic multi-beam data in sea state 3. Sea state 3 in 3 meters of seas. So these are very capable USVs, and they can, if we want them to, we can stay out there for 3 weeks at a time. We have satellite or 4G if we have it. There's also an onboard Wi-Fi for means of controlling. We have backup systems as well, so that we can still keep in contact with the boats. And we launch either by a traditional slipway launch, or you can use a crane, or we also have a LARS system to get the boats on and off larger vessels if we need to. This, in the good old days, this was our remote control operations centre in Carlingford in Ireland. Currently, the pilots and the surveyors are literally operating the boats from their homes. Each pilot has 3 screens to look at, one containing the camera imagery, another one containing the situational awareness and USV information, and then we have a survey output as well for the pilot and the surveyor to look at what's going on the sensors. This is all real time. We're operating 24/7. One of the nice things about operating 24/7 is around wind farms is that all the crew transfer boats go home, and when it starts to get dark, and you can move around the wind farm quite happily on your own at night, which is kind of nice. The USVs are equipped with various hull-mounted sensors. We can pretty much put anything on them. There's an underway CTD that we deploy from it. We've used, depending on what the job is, we pick the right sensor for that job. We also try and, with the USV pilots, we always have a human in the loop when it comes to navigation and looking out for safe, for other vessels and things like that. But the actual data collection we're trying to do as autonomously as possible. So the boat is an uncrewed but manned by remotely, but the actual operation we're trying to do as autonomously as possible. So to do that, certainly on the hydrographic wide area surveys, we're implementing the latest QPS Quincy auto swath system, which calculates the next survey line based on the previous sonar coverage. And that's within an area that we survey, and at the end of each area, the data is automatically stop logging, makes a new line, starts logging, so we can operate this pretty much hands-free all the way through the survey. We're also been operating multiple USVs to either maximize data gathering weather windows, or just to provide, because it's a more efficient way of operating. And all the data we've collected is for these surveys is to normal IHO Order 1A standards or special order, and it's all QC'd and verified by the various government agencies that collect that data. Some of the advantages of this are we've collected over 10,000 hours on the MCA Civil Hydrography program, which has been fantastic for developing the technology as much as also just the collecting fantastic data. We've done some large survey areas in the RSC, and we're currently in Lake Superior at the moment on a very large survey. And on that survey, all the data is being collected by this auto swath method. So in terms of line planning and all that sort of stuff, we don't have to worry about that. We just point it in one direction, and when it gets to the end of the area, it will automatically go down the next line, and we can specify an overlap that we need for it. We fitted the systems with sub-bottom profilers for doing asset inspections for depth of burial, but also for pre-lay geophysical surveys and things like that. We've used the standardizing on the Innomar standard at the moment with the 450s, which is giving us great data. And then we've also added onto the fleet of USVs, UAVs, drones, and in this way we can fly the drone at low water to capture as much as we can, as well as high resolution aerial imagery as well. And then we bring the USV in at high water, we overlap the two data sets together, produces a seamless model between the two. And then for the pipeline and cable engineers, they don't have to worry about trying to mix and match the land and the sea together, but they have one seamless model of the whole area. To put these technology in the boats into practice, some projects we've done. Offshore wind is growing, as everybody knows. We've spent a lot of time there. This year we've operated on these wind farms on the left there, predominantly doing asset inspection for monopiles, cables, but quite a few of those have also been for actually pre-route surveys for new infrastructure as well. The image there is from the Hornsey one, so we're 75 odd nautical miles out into the North Sea, and we're out there for a few days doing asset inspection for them. So this is some of the example of the data quality we get from the USV. So being 4.5 isn't any impact on the data quality at all. And say this was conducted in 3-meter seas as well. So so really high resolution data. For pipelines, we've done 1,600 kilometers of shallow water pipeline inspection. We've just finished 900 kilometers of that for BP out in Azerbaijan. This is a 10 centimeter DTM. We're using dual head R2 Sonic 2024s. It is a totally different sort of business model to running a manned boat. So we go up one side and we come back down the other, and you should have one pipe, and it should be they should join up, so you get a good data QC as well as good data quality from doing it this way. So we've also used the sub-bottom profiler for depth of burial, and we've also done trailing wire CP surveys as well, though that does require a human to be hooking the trailing wire CP up to the USV before it heads out. So not quite totally unmanned on that situation. This is a project we do for BP every 4 months or so. We've also done it for Shell and we're looking at other oil majors as well. And this is looking basically data harvesting, going out and checking the transponders on the seabed for whatever they're collecting. So this is a sort of a typical survey for us. We drive the boat up on this trailer up to Peterhead in this case, the harbour master, because he's interested in the boat. He helps shadow the boat out to the harbour just to make sure that, which is normally the area where you have interaction with people who aren't on AIS, like sailors and kayakers and people like that. So once the boat's out of harbour, we then take over control to the USV pilot back in Ireland. We then sail 128 nautical miles out into the middle of the North Sea. We interrogate those transponders. And one other thing, the very first time we did this, it was the first time they'd been interrogated and one of the transponders wasn't working properly. And we're doing this in conjunction with Sonodyne, and one of the Sonodyne technicians, she actually ended up in a McDonald's because they had better Wi-Fi than at home. She logged on to the boat. We gave her full access through down to her to the seabed transponders. She pushed a bunch of hex code down there, got the thing working again, and we collected the data. And because there's not much data when we're doing this, we can transmit that data back to the shore. Sonodyne check the data quality. They go, yep, we've got it all. Then we turn back and come in. Normally, we're not transmitting multi-beam data or anything because we need all the bandwidth on there for basically safe navigation of the boat. But we come in every week or so to download data. And that's it. So thank you very much for listening, and xocean.com for any more information or to get hold of me for any other questions. Thank you.
Thank you very much, Duncan. Right. So we'll now have 15-30 minutes open discussion, Q&A part. I will start with Matt Bates. I'll ask you a question for your presentation, and then it would be open for anybody to expand more, because we have a lot of similarities in the 4 presentations. And I'm happy we're having this session like that, so we can share together all the challenges and the benefits of this, which as mentioned by all of you, that it's part of all our interests as operators, as contractors, as manufacturers, and technology-oriented manufacturers that are available in the market. So you've mentioned, Matt, Horizon USV vessel with an ROV. Obviously, I agree with you. The area between the observation class and the work class ROVs, electric ROVs, are actually getting more blurry, and the gray area is bigger. And I would like to know, what are the main challenges that you have as far as the maturity of your concept stands now in terms of a failure scenarios, a fail-safe mode? You have a lot of variables, the loss of ROV telemetry. You have, if you have a TMS or a cage, the TMS telemetry failure, or if you have even a failure in the communication to the surface vessel or the telecommands. Do we have these scenarios in place, fail-safe mode, to be safe?
Yeah, it's certainly increasing. It's the shift has gone from sort of, if you like, dumb ROVs that are remotely controlled to more autonomous vehicles that have behaviors inbuilt. That ultimately the aim is to get to the point where you can break the tether and operate without the tether, and conventional ROV types of applications. So yes, along the way we have things like station keeping and fallback behaviours, so that should you lose communications, the system will just sit safely parked until communications is re-established. Yeah.
Okay. Obviously, this is something that we worry about for the telecommands. Also, as we try to reduce the complexity as much as possible for autonomous systems, is there any plan for tasks that requires more toolings? You mentioned in your presentation that you've touched on electric ROVs that are equivalent to 250 horsepower system of a conventional ROV. Would it be possible? Where are we in terms of the maturity of this? I'm trying to rephrase my question. What is the biggest or the most inclusive ROV with toolings that you have in trials or in concept on paper for USV that you would think can be put in testing in a stage that is close to now?
Yeah, so the Leopard ROV system is quite comprehensive in its tooling capability. We have torque tools and things like that which can be carried by it. It also has a reasonable size HPU, so it can operate most tools that are available on the market. And then the larger ROV that I mentioned earlier is soon going to have the capability for even getting up to being a blowout preventer type operation.
I was getting back to this point. We have a very high OPEX for our drilling operations because of the vessel that we have dedicated specifically for BOP intervention in case the rig ROV or the rig is out of the picture for any exposure reason. We would need this vessel to interfere and shut down the BOP and isolate. It can be an option to use a USV with a ROV capable of this intervention and can be around the field. I think this would reduce, would have a big cost reduction impact. Is this something you thought of?
It is something we thought of. Yeah, it's certainly possible, and we've got some ideas that can't quite share just yet, but some ideas for the future that will move us in that direction.
Okay. I'm not going to try to dig more in this. We'll wait for further updates. If anybody here would like to add or expand more, I think this can apply to everybody as well for the safe fail modes and all that. If anybody have any comments, please go ahead and share it with us.
Yeah, I was just going to fail safe is quite with the USVs is an interesting thing as well, because depending on what you're doing, sometimes normally if there's the default for communication failure is to go into standby mode and basically drift, or station keeping where you are. But if you're crossing a traffic separation scheme, that's probably not the best thing to do. So you want to then tell it to keep going. So you can't really have a default all the time. You have to, as part of the risk assessment for each project, as to what fail-safe modes you need and when to apply them. So it's quite, you have to give it a bit of thought sometimes as to what should be done. And then obviously to have backup systems as well to be able to talk to it if one of the other systems goes down. So
yeah, I agree.
Yeah, I guess you're right. It's subjective as well.
Yeah, I agree with Duncan that the idea of having kind of redundant communication systems that not only operate on different hardware, but may well operate on a different communications band should any problems, occur, not at the hardware level, but at the satellite level or at the band level. You need to have as much redundancy as you can built into these systems. And also to touch on something you said regarding the ROVs, I think you're right in that the difference between what we would class as inspection ROVs versus work class ROVs is becoming blurred. I think there are some really capable electric systems on the market these days, and certainly with uncrewed surface vessels, we're able to explore different commercial models for ROV operations. It used to be that you wanted the ROV to get as much done in a single pass as it possibly could because vessel time was expensive and unsafe and potentially very, very bad for the environment. Whereas with new USVs? Are we moving towards a smaller ROV setup and multiple passes for survey work, or multiple vehicles in the water to do intervention tasks? That there are lots of different commercial models you can start to explore when you remove a lot of the personnel from the offshore environment.
That's the thing. There is so many models now and so many concepts that sometimes I wouldn't say people get lost, but I would say that the focus is not quite there, because I guess every operator as well is focusing more on the concept that would think would be matching with their strategy for innovation and strategy for carbon dioxide emission and all that. But I guess you're right. For every concept, we have to really focus on the subject and what we would need for this in relation to what we have actually, what we can try in our offshore installations. So
I think it comes back to what Duncan was saying right at the start of his presentation about the idea of data as a service. You know, the idea that actually maybe a data purchase contract is simply the best way for clients to engage with those of us operating uncrewed systems, and then leave it to us as technology experts, as the operators of these systems, to decide the best way to conduct operations, whether it's one vessel, two vessels, three vessels. And assuming that the contract can be put in place as a data purchase contract, then it really does fall to the experts to come up with a methodology for that. And that allows exploration of different models, both in terms of acquisition, but also commercially.
Yeah, that certainly works for us on a number of occasions now, and it actually works for the clients as well. I mean, this paperwork-wise, it's, you know, there just isn't any. It's like a two-page contract or something to get it done. And also the other advantage for us sometimes is that you know, it is new. Every time we go out, it's, you know, you learn something new. It is new technology that we're dealing with all the time. And the last thing you want to be doing is being pressured by a client to put the boat in the water when you really don't want to put the boat in the water because you don't think it's right, but the client thinks so. So when you eliminate that and you go to, you know, the lump sum basis and the data as a service basis, then, you know, it's more beneficial for us actually operating it to get to optimize the, you know, to do it when we need to. Obviously, you've got to do it within a certain time and to certain conditions, but you're not having that sort of day rate push like you used to.
Yeah. All right. I would like maybe a quick one for Al Romson. It was about the unmanned pipeline inspection that you have mentioned in your presentation. I think that the project was Equinor with the Hugin. It was 350 kilometers of pipeline in 30 days. So as we go back to one of our main reasons for going through all these new technologies is the cost. So for this business case side of the project, what is roughly, I'm sure maybe you've done this exercise, I'm not sure, but what is roughly the estimated cost saving for the pipeline section for this project, for example, or any other project you would choose in comparison to our conventional operations, vessel plus ROV or whatever? And I think this can also goes to Duncan as well, and for the pipeline inspection project you've mentioned as well.
Yep. So I think outlined in some of the slides, real cost saving there is taken, like for all these methods, taken away this large vessel and the number of crew, and it's not just the factor of having the large vessel out there and all the associated crew changes and overhead in the office to support these operations. It's also the automation of the processes, which is a big part of this. So a big part of what I was talking about there was not just the physical operations of between the AUV and the USV, but the software running on board there, which at the time we were dealing with IVA and looking at how we can sort of have like data processing sort of initiated on the vessel. And we didn't get to the stage where everything was complete on the vessel. There's still some work that needed to be done when the vessel came in and we downloaded the data sets. But to us, that's a big factor because it's reducing turnaround time, making the data available. So you're talking about data as a service, you know, that service is available more timely to the client. So yeah, there's another question that sort of springed up in my mind when I was watching some of your other presentations is what are the options you've either been using or you're thinking about using for data processing on board. Michael, I think you mentioned in your presentation about optimizing the processing side. Have you got in-house capability or you decided on sort of routes for this?
Yeah, I mean, Ocean Infinity, as well as being a vessel operator and data acquisition company, we have a lot of our own technology. We have a lot of our own IP around that. But our model, rather than building something from scratch, which can be time-consuming and expensive, is if there are products on the market that are 85, 90, 95% of what we want as a business, then we will open up dialogue with those providers. So we're working with Iver on the Armada interface to basically take what is already a very good package from Iver. We all know that, but certainly it's something that regarding kind of optimizing for true uncrewed operations in the way that we're intending on using it, needed a little bit more on it because it's some quite niche stuff that we're looking at. So we've taken 90% of what Iver have provided and an off-the-shelf capacity, and then we're working with them to develop kind of some niche and individual modules for that. So yeah, certainly it needs careful attention, and certainly the need to not only be able to acquire and look at the data across a satellite link in real time, which is no mean feat in and of itself, but also that kind of extra level of quantifiable and removing the subjective nature of some of the assessment is something we're really keen on, to provide a really easy snapshot of exactly what's going on at any time.
I think it also depends on what type of survey you're doing, because yeah, I mean, I think, and it also depends on how your boat's being driven, because if you're so doing pipeline stuff, yeah, Navier model's a great piece to equipment for doing that. But if you're doing a big area hydrographic survey, it's not the one you want to use. And we're driving the USV from the survey software. So then the survey software, the online survey software, is really important to the whole thing. And the more you can do with that, the better it can be. So we're currently using Quincy online, but that's not to say we're always going to do that. It's we have a list of requirements that we need the software to do. Our IP is in the over horizon control software for the USV. That's our bit of it, but we can still interface that to others, to the acquisition software as well. So yeah, we have a list of requirements that we need the software suppliers to do, which they don't currently do. So it should be beneficial for everyone, because I think at the end of the day, most of us are needing the same thing. So whoever does it first should get it. Should get an initial jump on everyone else.
Right. Just to expand a little more, I'm glad, Al, you've asked this question. When we try to promote for innovations or for new technologies that can help us I'll put it as simple as that. I'm based in the headquarters, for example, and we are promoting for all these innovation technologies for our affiliate worldwide. So we have so many affiliates that would like to use new technologies for the old fields, for the survey, for the IMR operations, for pipeline surveys and all that. And in order to present this case, we need to present the cost saving roughly percentage. We need to, of course, express how this is good for the carbon dioxide emission and the personal movements and all that. And of course, the processing of the data is part of the process, because this is time, and time is cost. And this will actually, the people exposure, of course, this is another big subject. I'm trying to say, I don't want a number. I'm trying to say, do you have a percent? I know that in your presentation you've mentioned all that, but do you have a percentage in mind? would it be for a 30-day campaign like you have done, like 50% of the cost, or it's not that big of a difference? It's more like 80 to 90. It's more like 20% difference for a conventional system, but we will have to use other benefits to convince them. If anybody have any of these, would be great to really hear your positions in this.
It's varied a bit. We don't often.
I mean, it's a business case. If it's done, it's done.
We don't get to see quite often what other people have put in price wise on it. But I know on some of them, we've recently been. I think we were 2/3 of the price, or it was either 2/3 or 1/3 of the price. It was significantly less anyway than what they were expecting to get, and what they compared it with before. But it does vary a bit on how long the survey is, and what's involved with it. Because in some ways, the longer the better, because you can sort of get into it a bit more, and all your mob costs are much smaller. Not our mob costs are very big, but yeah, a third is
the crew changes at
the moment, I think.
Right. Okay.
I think
that's good to hear.
I think I'd like to take the opportunity to flip that question back as a representative of an operator. And I guess the real question that we ask our clients is what's your main buying motivation? Is it truly a cost saving that you're looking for? Or is it actually a more sustainable option that you're looking for, or a safer option that you're looking for, or a more efficient option that you're looking for, reducing time offshore, reducing campaign length? Because each of those has obviously different motivations, and we understand that. And not all uncrewed operations are cheaper, as Duncan said, but most uncrewed operations are more sustainable. They're certainly safer. They're certainly more efficient. So I guess my question would be, if you can receive the same service that is carbon neutral and safer and gets done in a shorter period of time, are you also expecting a cost reduction? Or would you rather have the survey that takes the same amount of time, produces the same amount of emissions, and produces the same HSE exposure, but for less cost? Or is it somewhere in the middle? And that's an open question to anybody, really.
I have my answer. I have my answer straight away. If you ask me personally, if you ask me for my position, definitely, if you are using the same, even the same time and the same cost, and we're having better we're having better process for the environmental and safety, HSE and the personnel exposure and all that, I would definitely go. It's part of our mission to go for the safer option, of course. But if it's cost better, that can make the eyes go more blurry when you are talking.
Of course,
that's what I was asking. But obviously, we are very much interested in this.
Yeah, and different projects have different answers to that question. I fully appreciate that. Sometimes you need a project completed cheaply, sometimes you need it completed quickly, sometimes you need it completed in a more sustainable fashion. And I'm not suggesting that there's one answer that answers all of those questions. And as Duncan said, I think you have to look at it on a project by project basis, because that's the only way to properly assess which of those factors is the most important. But broadly speaking, is uncrewed technology going to lead to a reduction in cost over time? I would imagine so. But that's not to say that every project will be cheaper just because you're operating uncrewed systems.
Right. Okay. We gotta wrap it up. I stay with you, Michael, real quick. We have 5 minutes, so let's get this in a quicker way. You have your system allowed. That's what I told you. We're waiting for your demonstration. We would expect from you to have much longer autonomy compared to in terms of the battery solutions, full battery solutions, compared to whatever is proposed by others in the market. The associated reliability for the endurance claims, we are really waiting for this to be fully demonstrated. Armada fleet is in the testing phase. What are the main challenges in operating these USV in terms of developing longer autonomy? Are you combining the solar energy with batteries? What did you do to get over these challenges?
Yeah, sure. So I mean, firstly, on a pure fuel tank capacity, the A21 will do almost 3,500 nautical miles. at cruise speed, and the A36 will do 5,500, and that's important because, as I said, we're designing them to be able to transit across oceans. But we also have quite a large battery capacity involved in each vessel. They'll be able to run silently with zero emissions for short periods of time. So yeah, we have batteries on board. We're also looking at retrofitting the larger class, the A36, with either hydrogen or ammonia fuel cells in the future. So yeah, certainly investigating, new and futuristic fuel options. We did do a design loop with the A36 and seeing whether we could turn it into a hydrogen vessel from the day it launches. However, the availability of hydrogen all over the world is not necessarily as prevalent as marine diesel. You can go and get diesel in pretty much any port in the world, whereas there are some parts of the world where we're certainly looking to operate where hydrogen fuel is not as available. As those futuristic fuels become more kind of omnipresent around the world, I would imagine that you'll see more and more ships, not only in the uncrewed systems, but also with conventional shipping that kind of look to use those more modern fuel technologies. But no, certainly we're very much focused on using the latest and most modern technology to give the greatest benefit to our clients. And if that means retrofitting for hydrogen or ammonia in the future, then so be it. But certainly initially they'll have some pretty extendable ranges. Because that's what they're designed to do. They've got really efficient diesel hybrid engines in them. So from a conventional fuel tank, they'll be able to do some serious kilometerage before the fuel runs out.
Okay, that's great. The last question, it's for everybody. It's a general question. I will start maybe with Duncan and others. Is about the resistance we get from our partners when we're trying to use AUV technology for some survey operations. Obviously, which is the main reason we have it, is that we can't control the operations based because we are not on real time. So we'd have to wait, and then if there is something, we have to actually mobilize another vessel to remove it, or if there is some repairs or if there is some debris that need to be removed, we have to get another vessel. So that's a basic question, but that's why a lot of our partners are not really pushing for this to go, because you want the safest one, which might be more costly, but at least we will have the full operation in one shot rather than getting the operation not in real time. So give me your response. If we have also a combined system, something like a USV with a small, with a AUV and maybe another ROV on board that can have this tooling mechanism that can help and support if it's needed, or something like that, that would help us.
Yeah, and I mean we've looked at launching AUVs or having ROVs from the USV, but to be honest, at the moment, there aren't that many pipelines in the world fundamentally, and there's an awful lot of wind farms, and those wind farms are in predominantly less than 40 meters of water for most of them. And what our first goal, our main goal, was to develop the over-the-horizon technology and the communications, and to be able to to do all that. Once you can do that, then you can easily scale that to a bigger boat and all the rest of it. And so towed bodies and things like that. That's what we're going to be doing. That's our next step, and that's pretty soon. But we actually find that once we do a survey for someone like yourselves, then that department then starts talking to the other, and we find that our best marketing is actually done internally by the different companies. It's great, and then then some of the other companies go, oh well, you've done that, oh we need to give you something. So that it is a bit of a ball rolling. Once someone's got in there and you've done it and you've shown that it can be done and the quality is better, if not the same as what a normal survey ship can do, then it does roll on. We don't really have any the biggest holdback has actually been survey companies, in terms of survey companies which have survey boats, and none of the survey companies that actually have manned boats really want to move into this
We have 30 seconds to wrap up. Sorry.
Yeah, sorry. But that's But yeah, we don't have that much.
Okay. Yeah. No, I understand. Anybody have any comments? 30 seconds each, or anything to add, to expand?
Doug, you mentioned the towed vehicles, and that's definitely on the agenda for us. We're looking at assessing the feasibility of same sort of pipeline surveys by using towed vehicles as an option instead of AUVs. So that's potentially one avenue.
Okay. Okay. We'll be happy to listen, to hear about it.
Yeah.
All right, everybody.
Right.
Thank you very much. Thank you very much for all these presentations, and it was very valuable. And I would hope to this presentation will be online in the beginning of December, and obviously we'll get questions, and then maybe you would reply to the viewers. Thank you very much, everybody.
Excellent.
All right. Thanks all.
Thank you.
Yes.